All right, welcome back. Today I'm going to talk about machine learned potentials and automatic differentiation in molecular simulation. Hopefully you can all hear me, and I'm only saying that because I'm trying something new, and there's always things don't always work as you plan. Okay, so today this work was done mostly by Jacob Bose, a former PhD student of mine, and Yilin Yang, who's a current student. And it's funded in a combination of NSF through CBED and the DEMREF and the Department of Energy, Basic Energy Science. So let's get started. The idea that I want to get across today is related to molecular simulation as the application, and I want to tell you a little bit about how we think about molecular simulation. So typically we use equations to simulate materials and material properties, and we do that for a lot of reasons. We want to understand materials, we want to discover materials, we want to design materials, and develop new knowledge about what determines their properties. And that goes from this nanoscale, atomic nanoscale down here, all the way through this mesoscale out to quite large scales that are like centimeters or meters in scale, and different time scales down here. The time scales are quite short, 10 to the minus 15 to 10 to the minus 12 seconds, for example. And then over here we get into progressively longer time scales, like for oxidation of a metal in a bridge, we're talking about years of time scale. Now, anytime you hear molecular simulation, there are equations, and you should ask, where did those equations come from? So in the beginning, there was math, and then there was physics. So in the late 1600s is when Newton's laws of motion kind of got started, where there was a formal relationship between, say, force, mass, and acceleration, F equals ma. And from that differential equation, you can predict the motion of large bodies. And it was only in the early 1900s that we started being able to develop equations for atoms and behavior of atoms and electrons. So in 1913 is when Bohr proposes his model of an atom, which was kind of like the Newtonian or Kepler view of planets going around the solar system, but these electrons that are going around in orbitals. And the critical difference between that and classical mechanics was that these orbitals had discrete nature. So there are only certain orbitals that the electrons were allowed to go around in. Then a short, little more than a decade later, Schrödinger derived his wave equation that's shown kind of over here. And this was a new way to think about electrons. And around this decade, Paul Dirac kind of famously said, this is the only equation we need. It's perfectly exact, and the problem is that it's just too complicated to solve because this equation has so many dimensions, multiple dimensions for each electron, and that makes it difficult to solve. Now, it took several decades more, till 1964, before we reformulated that quantum mechanical point of view into density functional theory. And this changed our point of view from looking at the interactions of every electron with every other electron to looking at the system as a function of electron density. So it drastically reduces the dimensionality of the problem, and that came with the cost, though, that we had to make quite a few practical approximations to the physics. So although we know in theory or in principle more or less the right equations, there are several things in the exchange and the correlation of electrons that we have to make approximations. So this was awarded the Nobel Prize in the 60s for, no, not in the 60s, but the discovery from the 60s was awarded a Nobel Prize with John Pople. And since then, Moore's law has just relentlessly increased the amount of computing power that enables us to do more and more of these computations. In parallel, for the last 90 years, we've had a search for an alternative in the form of molecular force fields. And these are mostly analytical physics-based models that describe the interactions between atoms and molecules. And that, I'll show you, has run into kind of a wall in terms of accuracy and capability. And so we have these two approaches. So my group for the last 15 years or so has primarily been a DFT group where we use density functional theory. I'll tell you a bit more about it in the next slide or two, to make models of atomic and molecular systems, calculate energy and forces. And you can check out this book over here that describes a lot of how we do those things, mostly using VASP in this book. So with DFT, we can calculate things like adsorption energies, reaction barriers, density of states, band structures, alloy phase behavior, bulk equation of states, and many, many other things. All right, so what is DFT? If you're not in the field, it might seem kind of magical. And it is kind of magical. We set up a model system like this, where each of these like light gray balls is, say, a silver, the dark gray ball might be palladium, the little red ball here might be an oxygen, and this is a model now of a slab in a unit cell. And this unit cell is repeated in all three directions so that we have a continuous slab in the x and y planes, and then these surfaces are separated by a vacuum space in the z direction. And what we do with density functional theory is calculate the total energy and the forces on all the atoms in this system. And we can combine that with optimizers to find the lowest energy of the system, and then combine it with thermodynamics to calculate things like reaction energies, reaction barriers, phase behavior, etc. And the real issue with DFT is mostly that it's slow and expensive. So this unit cell might take many hours or days to calculate, and we rarely need just one of these. We mostly need like thousands of them these days, or hundreds of them. And so we need to figure out ways to expand and leverage DFT, and that's what I want to talk about. Now, one of the things people have used are physical potentials, or atomistic, molecular potentials, force fields. These are kind of similar names for the same thing. And you might be familiar with things like the Lennard Jones potential, or Morse potential, Comb potential, Rex force field. These are all kinds of models with more or less kinds of sophistication, and they describe different kinds of interactions like hydrogen bonds, or charges and Coulombic interactions, etc. And typically they need to be fit or parameterized from some source of data. And that could be experimental data, or it could be DFT data. And what I want to show you why we haven't gone down the road of physical potentials ourselves is over here we have a DFT predicted energy and a force field predicted energy for vacancy formation. So what is the energy to create a vacancy in some solid? And you can see the parity line here, and the agreement between them is not great. And it is fair to ask, how good is DFT at this anyway? We know we make approximations in the exchange correlation functional. So is it a big deal? That's a fair question. The critical point is whether or not we believe that there are systematic errors in DFT that largely cancel, and whether or not we believe we can systematically improve the exchange correlation functional. And that has been happening, and is like a long, interesting argument that I don't want to get in here. What I do want to get into the idea, though, is that we can generate much more DFT data than we can experimental data across a much broader range of conditions, and that makes DFT an interesting source of data for fitting these parameters. And the other thing is, if we look over on the right-hand side, we see for surface energies that we have force fields on this axis and DFT energy on this axis, and again we don't get very good agreement across this, and it's very difficult to improve these because the physics is quite complex. So the physics here is not at all easy to write down equations for, and so that's one of the reasons why we're not able to systematically create a better Lennard Jones or a better Comb or a better Rex force field without also making it as complicated and expensive as DFT. So what that has led me to is the need for a new and better way to leverage DFT. And so the approach that we've taken is to find a way to use machine learning to build these models. And that's shown kind of in the idea here. We have force fields over here that are probably now nearly a century old, very well developed, and not a whole lot of room to add new things. We have over on the right-hand side, DFT, comparatively young, and there's room for improvements over here, but this terrain is quite steep and quite difficult to work in. And what this picture here is Pittsburgh, where I am. This is the point down here, and we have a city full of bridges over here across these two rivers. CMU's back here in the background. And what we want to do is find a bridge using machine learning where we have machine learned potentials in the middle that combine the speed of force fields and what we think of as the accuracy of DFT. So that's how we're going to proceed. And now I want to show you what is tricky about this. So on the left-hand side over here, we have the conventional classical potential. And the way I've thought about it is we have Cartesian coordinates and the identity of atoms as our inputs to a model. We have some very nonlinear, complicated equation that gives us atomic energies. And once we have atomic energies, we sum them up to get the total energy. That's how a lot of the potentials work. And the problem is this spaghetti in here that we don't know exactly what that nonlinear transformation of coordinates to energies are. In machine learning, we kind of turn the problem around a little bit. We have the same input, Cartesian coordinates and the atoms, and what we do is calculate something that I'll call a fingerprint. And so this fingerprint is a numeric vector that's going to be, let's just think of it for now as some transform of xyz into a vector. And that vector we're going to feed to a neural network. Could be another machine learning algorithm as well. But this network is just, the way I'll describe it, is a tunable nonlinear transform that we find by optimization. And the point of the transform is to convert the fingerprints from this space into a new space that the atomic energy will be linear in. Right? So I'll show you how that's going to work in the neural network in a minute. But once we have the XYZ to fingerprint through the neural network to some new linear space here, then it's easy to do linear regression to get the atomic energies. Okay, so what is machine learning here? On the left, we have the common portrayal that it's some kind of mystical machine learning algorithm that is like a human mind and outputs wisdom. But what I want to emphasize that real ML looks more like this equation, not like this kind of graph over here. So this equation is just the equation for one layer of a neural network that has a linear activation of the input x, so wx plus b is like a linear activation. Then we take the tan h of that vector to get the nonlinear version of it, and we do a linear combination of the output. That's it. We have a linear transform inside a nonlinear transform with a linear proportionality on the outset. And the w's and the b's are called the weights and the biases, and we find these by optimization. So we just fit this equation to some data that we have. X will be the fingerprints that I described, and we just have to minimize something like the sum squared error or the mean absolute error or the root mean squared error. And if you're a machine learning guru, then we can add regularization to these parameters to give them, whatever properties we want. But if you're a regular engineer that's familiar with regression, you should see this as some kind of nonlinear function, and we're just going to do regression. All right, so I think it's helpful to think about neural networks before we get into what they do, and ask what are they? Why do they work so well? And I'm going to show you a couple of different points of view in the next couple of slides. So let's start out with this idea that neural networks are like something old, something new, something borrowed, something blue. On the left, we'll talk about a Fourier series. So the Fourier series expansion, you'll probably have heard about. This is taking sines and cosines as a basis set, and you can expand any periodic function in terms of the sines and the cosines. And there's a couple really cool properties about a Fourier series expansion. One is we have integers on these inside arguments, and that makes these functions orthogonal to each other. And that orthogonality leads to this set of equations down here where we can calculate what the coefficients of expansion are just from these little simple integrals. So we now can take any function and calculate the Fourier series expansion with just evaluating these integrals. And that's important because we are not doing fitting when we do that. So now let's go from the Fourier series and take a couple of steps. Let's get rid of the sign just for convenience for this and draw the remaining partial Fourier series as a graph. So this is like a graph form where we have the input x and it's going into one layer, and each node here is going to be one of these x, 2x, 3x, so forth to nx, and we have the expansion coefficients that are multiplying each one, and then we have the final output. So this is just a graph form of that partial Fourier series expansion. And now to go from this to a neural network, we just have to make a couple of small steps. One is, let's relax the integer requirement here and let this be a float number. Now that has a semi-important consequence, and that is when they're not integers, when they're floats, these functions are not orthogonal to each other, and that means that we can no longer use these expansion coefficient formulas, so we have to fit them. So step one, relax the integer constraints here, and then step two, let's change from cosine over here to tan h. And now we have on the right hand side a pretty typical looking neural network that has all fitting parameters and an expansion basis set of tan h. So one way to think about a neural network is that it's like an expansion of data in a basis set. It's obviously truncated because we can't have an infinitely wide neural network that we're going to write code for. But one way to think of a neural network is just like that. Okay. All right. The second way I want to think about neural networks is to think about the flexibility and the capacity. So I show in here these are French curves. They're used in mechanical drawings or drafting, and they're used to draw smooth lines through a set of points. And this idea came about in a chat with Zach Ulysses, one of my colleagues, that all of these neural networks, they have lots of curvature that can be represented by different choices of the parameters, the weights and the biases. And the trick is, how do we find the part that matches the data we have? So if we have these data points here that are the points we want to fit, then what we're trying to do when we fit a neural network is to take these French curves and then rotate them. Right? We're going to rotate and translate them until we find a part that fits, and now we can smoothly interpolate and predict in that region quite well. And the important thing to think about here is that outside this region, like all of this, has nothing to do with the data. Like these regions aren't constrained to fit the data. And so any prediction that we make outside the data range is not likely to be good. That's a regular thing that chemical engineers know, and other engineers know, that when you extrapolate nonlinear models, they don't always extrapolate reliably. And these are not different. They don't extrapolate outside the data very reliably. Okay, so let's take a brief tutorial example just to give you some clear points on how this works. So this example is looking at bulk copper polymorphs. So we're going to see the FCC structure, BCC structure, simple cubic structure, and a diamond structure. And these are all bulk structures, and this data in the graph shows you the equations of state, how the energy of them changes as a function of the volume. So what I'm going to do is take this region down here in the square, and we're going to build a machine learned model that can predict these data, and then we're going to see how well it works on the data outside. So inside this square we have 200 data points, outside this square we have another 200 data points, and we'll be able to see the performance. All right, so the way we do this is using a neural network. This is the Baylor-Paranello kind of scheme, where we have a fingerprint vector that's here. I'll tell you about that in a minute. We typically use a two-layer neural network, and so we have hidden layer 1, hidden layer 2. These are both nonlinearly activated, And you can think about it as taking this G vector and then transforming it into this vector. So this is going to go from 3 elements to 5 elements, and then we do a linear combination to get the atomic energy, and that is done for each atom in the unit cell. All right, and then once we have all of the atomic energies, we add them up to get the total energy. So how do we create the G vector? So the G vector is a local environment that is a set of numbers that represent what's happening around an atom. So if we take this atom right here, we have to ask how would we characterize what goes on in here? So one way we could think of that is inside this circle, how many white atoms are there? I would count 4. And how many black atoms are there? And I would also count 4. So those are 2 numbers that characterize what happens in the local environment around this atom. You could do a whole bunch of other things. There are radial functions that look at radial weighted distributions. We can have functions that look at the number of triplets and the angles between them, etc. And you just have a set of these numbers that give you a fingerprint for it. And that is what we use as the input to the neural network. So here's an example where we use Chebyshev fingerprints. They're one of my favorites. And here we have, say, a dimer, 2 atoms that are separated by a distance rij. And then we have in each one of these lines various Chebyshev polynomials that depend on that rij times the blue line, which is a smooth cutoff function. So what that tells you is that, let's say we have an rij of about 3, and we have 1, 2, 3, 4 of these functions. Then we have a fingerprint that is given by these 4 numbers that are indicated by the blue lines. And if we have it at 2, then we would get these ones. So at 2, we would have this number, this number, this number, and this number. And that's not the same. These should be down here, like so. And so we have these fingerprints that are specific to the local environment. And we can have as many of these as we want. If you want a 10-element vector, then you just have 10 polynomials. There are lots of these kinds of fingerprints to use, and basically they all kind of work. All right, the next thing that we do is we have to scale and normalize the fingerprints. So there's a bunch of ways to do it. We will often scale them from 1 to -1 or 0 to 1. Again, it doesn't really matter as long as you do the scaling. Here is the raw kind of distribution of fingerprints that we get. So in the example for copper, we have 10 different fingerprints. I think these ones are radial, and these ones are angular. Right, and it's not super critical what these details are, but we get a distribution of, these are violin plots of the 200 different training points that we use. And the scaling is important because if you use tan H as your activation function, they saturate outside about ±1. And so you want to scale the fingerprints to be in that range so that you don't run into training problems. So the training is really standard machine learning stuff. We use gradient descent. We typically randomly initialize the weights. We can do anything from 90-10 train test split or 80-20. None of those details are super interesting. And we have to do several epochs of training so that we change the weights to reduce the objective function. So here's one example of a small neural network that fits this data. This is a training curve over here that shows the mean absolute error as a function of the epochs. You can see it goes down. This is on a log scale, so over here the errors are changing quite small and are in the milli EV per atom kind of range. This is the distribution of those errors at the end. And we look at 2 things. One is what's the distribution of train errors and what's the distribution of test errors. And we want to see that they look kind of the same. And these are not scaled because there's different numbers of them. But you can see over here at the milli EV per atom level, these are about the same. And then here is the parity plot. And what we want to see in the parity plot here is the test and train data being on this parity line, and we want to see a good distribution of train and test across here so that we know that they have similar distributions of fingerprints. Okay, so let's talk about making predictions now. So we take our machine learned potential, and in this region right here, we get excellent agreement between what we know is the truth and what we would predict. And that shouldn't be a surprise because we fitted it to work in this region. And then in this region, as we get further and further away in this way, it gets worse and worse. And if you are, an optimist, you would say it's not too bad. At least it's all the right sign. But especially this data here, you can see is not predicted very accurately. And the problem is that this is an extrapolation. We're very far from what we know. And as I showed you with the French curve example, there's no reason for us to think that it should be very accurate in that region. So we could add that data and train back to it. Now we will find a new part of the French curve that fits. But that's not really the point at this time. Okay, so how do we know it's extrapolating? What does extrapolation mean here? We have a 10-dimensional fingerprint, and in what we have here are the training distributions in blue, and here you can see the prediction is in orange. And what you can see, especially in regions like these, that we have prediction fingerprints well outside the range that we trained in. And that is a as clear as we can say about extrapolation in high dimensions. So we're either extrapolating or in a region where we don't have a lot of data, and either one of those is bad when it comes to making predictions. So you really want to make sure that the predictions you're making are within this space that you have trained in for these. All right, so I want to switch now and talk about alloy surface stability as an application to show you how we use this. So the idea is that we have a bulk alloy surface here, and the surface can exchange with the bulk. So it can take a surface atom and exchange with a bulk atom, and we can also consider adsorption. And whether or not these are favorable mostly depends on whether we lower the energy or not. And that's what we want to calculate. So what I would like to do, did I miss one? What I would like to do is use Monte Carlo for this. So we would like to have a simulation that exchanges the atoms and allows for configurational entropy and gives us a large slab so we can get a high accuracy in the calculations. Now this slab is 10 by 10 by 15, so that's 1500 atoms, and that is way too big for DFT to calculate the change in energy. So what we're going to do instead is train a machine learned model that we can use to calculate that. And so when we make a swap, we'll use the machine learned model to calculate the change in energy. And if it's negative, then we will accept it. And if it's positive, we just accept it with the right probability that is determined by the Boltzmann probability. And then we just run that until we get steady state. So the example that we worked out for this is looking at palladium-gold segregation. And palladium is very active, gold is not, and gold tends to prefer to be at the surface. So for example, here we start out with the bulk composition of gold 40, palladium 60, and as the Monte Carlo runs, what you see is that the fraction of gold goes from 40% up to about 78%. And in the second layer, it is depleted. Right? So what's happening is the second layer gold atoms are moving to the surface, and the palladium atoms in the surface are moving into the second layer. And we can do that now across the entire composition space. So here we go from 0 to 1 in gold. And this trend here is what we see in terms of the gold surface composition. So across the entire space, we see gold segregation, and even the curvature is reflected in the experimental points here using this Monte Carlo simulation with the machine learned potential to do all of the work. All right, so that was just a short discussion because I want to finish the talk by telling you some interesting things that we can do with automatic differentiation that's related to the machine learning. So here we have shown we can use machine learning with DFT and statistical simulations like Monte Carlo to model more complex behavior. But I'll point out we need accurate DFT, we need the right training data, and we need the right simulation to get the right results. And if you don't have all three of these, then something about what you do is not going to be totally right. All right, so I only touched on one aspect of machine learning and catalysis, and only one kind of machine learning at that. There are lots more, and you're going to see a lot of applications in spectroscopy, in screening, in microkinetic models, design of experiments, etc. So this is a very rich space to pay attention to. Now, I want to finish the talk and say, like, how is all of that possible, and what else can we do with it? And I think the way to think about machine learning is it's just a new way to do model building. And what we've seen is a couple of decades now of research in software and hardware converging that really results in a democratized kind of accessibility, and it has implications way beyond machine learning and molecular simulation. So let me finish the talk on that. So what is automatic differentiation? So at the core of machine learning is optimization. That's what the regression model, the training, we are minimizing some kind of loss function, the error function, and that is using a gradient descent algorithm. And the gradient is always calculated by automatic differentiation in the most modern frameworks like TensorFlow and PyTorch. So what is automatic differentiation? It is a way to compute derivatives of programs. So it's not numerical differentiation, and it's not symbolic differentiation. So the first one is where you try to approximate your derivative by, some f of x plus minus f of x plus delta h divided by delta h in some limit of delta h goes to 0. That's a pain, doesn't work in high dimensions, and is not very stable as delta h goes to 0. It's not symbolic differentiation. You might be familiar with Maple or Mathematica, and those have a way of calculating symbolic derivatives, and they often are not very good for what we need. So what automatic differentiation is an application of the chain rule to a program. And it's now a standard feature of all the machine learning frameworks like TensorFlow and PyTorch, Chainer, and some others. And I think it's going to have a lot of roles in molecular simulation and science. And what's new about this is that it's basically become commodity programming language like Python and Julia and others. And the high availability of compute power makes it practical for us to think about it. So let me give you a nutshell example. Let's start on the left. We have, let's say we have this program that is designed to calculate the Arrhenius law. So we have, the rate is some pre-exponential times e to the activation energy divided by r divided by t. So what we do is write this in a series of steps where we take this and express things in terms of W1 and W2. W1 is obviously K, W2 is EA, and then we can express this constant as W3, and then this product is W1 times W4, and this product is W5. And so if we ask what is the derivative of the rate with respect to the activation energy, that is equal to dW5 dW2. So that's just regular calculus, and the way we apply the chain rule is we first start out with the variables like this. Those derivatives are 0 and 1, which is dW1 dW2 and dW2 dW2. And then we just apply the chain rule into these. That's shown on the right, and that leads us down here to the actual derivative that we want. So that is what you would do by hand, more or less. Here it is in practice. I use AutoGrad here. It's one of my favorites. It's kind of old, but it's simple. So we import grad. We write a function here that has an argument k and ea. And then down here we have one line. We take the gradient of our function r with respect to argument 1. And remember in Python the arguments start at 0, so this is the this corresponds to EA. All right, so 1 is this position right here. And then this returns a function that we evaluate at the conditions we want. And you can see here the analytical and autograd derivatives are functionally equivalent. So we have one line that gives us the analytical derivative that we want. So why is that important? It's because derivatives are everywhere in scientific programming. They are in optimization regression. We use them in thermodynamics for pressure and other thermodynamic properties, forces and stress, I'll show you that, elastic properties, and many, many more. We can have automatic differentiation that helps us with all of these. So let me wrap up with an example. There's a function that I defined over here that implements this Lennard Jones potential in using JAX, which is similar to autograd. And this takes some parameters that are the sigma and the epsilon. It has positions and a unit cell. So if we want the potential energy here, we get our parameters, we calculate the distances, we do a bunch of kind of vectorized operations down here to get the C6 term, that's this one, and the C12 term is just C6 squared. That is how we got to the 12 in Lennard Jones. Then we sum up all the atoms and we divide by 2 because we double count all the atoms, and we return the energy. So this function by itself is not the critical point. There are no derivatives in this. But if you give this function the parameters, the positions, and a unit cell, it will give you the total energy. Now, this is where it gets exciting to me. One is, if we want the forces, we know that the forces are just the negative derivative with respect to the positions. So we have a function get forces of the parameters and the positions in the cell. We have a one-line derivative here, and then we just return that derivative evaluated at the positions in the cell, and that's it. Those are the forces on those atoms. Fully vectorized, automatically done. Now I can add anything I want to get potential energy. As long as it's differentiable, I don't have to change this function for forces. Similarly, we can get the stress. The stress is just a similar kind of tensor derivative of the total energy with respect to displacements of deformations of the unit cell. So again, we have a function that gives us a parameters, position, and cell to get the stress. We calculate the volume. We have one line to get the function for the derivative, and then we just evaluate it at the place that we want. This makes it symmetric, and then we return the stress elements. Again, we just change anything we want in potential energy, and this automatically propagates the stress correctly. And then finally, the vibrational frequencies. This is also pretty exciting. This allows us to calculate the Hessian. The vibrational frequencies are related to the frequencies of the diagonal of the Hessian. And so here we have one line that gives us the Hessian of our potential energy. We get the diagonal right here and multiply by the masses. We get the eigenvectors and the eigenvalues. And the frequency is just a scaled version of the square root of those eigenvalues. So that is a remarkably simple way of getting vibrational frequencies, especially if you have ever tried doing the finite differences to approximate the diagonal modes yourself. So this also doesn't have to be changed. We can add anything we want to that potential energy to add different physics, etc. It makes it very easy for us to test out the influence of things on any aspect of the derivatives that we want. Okay, so let me finish up here with the outlook on machine learning and science. I think automatic differentiation is a new paradigm in scientific programming and model building. I didn't talk about it very much, but it enables physics-based models with derivative features and constraints. We can simultaneously fit our data to the energy and to the forces, or we can invoke different kinds of derivative constraints like Gibbs-Duhem equations, for example, etc. And this is really like a new way to think about the model building. I think there is a long way to go before the science in our heads resembles the code on the screen. And that's really a problem because we have to do this like translation in our minds of like, here's the equation I want, here's the AutoGrad code or the TensorFlow code or whatever. And they look so different that the impedance mismatch there is limiting what we're able to articulate in our programs. All right, so I'm going to wrap up there and just acknowledge again some people in my group. Yilin did some of the work with Ankit, and Mingji and Jenny have made other contributions. The funding from CBET and DEMREF through NSF and the Department of Energy, and a couple of collaborators. And I think that is a good place for me to stop and invite questions through the chat. And if there are none, then thanks for coming, and hopefully we'll see each other in person before too long. All right, so any questions? All right, so Mehul's asking about whether machine learned potentials provide enough physical intuition about the process. So the potential itself provides zero physical intuition about the process. The actual model is just a like a truncated expansion in your activation function space, and that isn't physically motivated at all. So in that sense, it doesn't really give you any more insight or intuition than just the energy and forces from DFT do. DFT is like maybe a smidge better because you could also try to dig into the electronic structure that comes out of it, and you might get some intuition from that. But on its own, the energy and forces alone don't give you any insight. So what we've done is combine it with things like Monte Carlo that are simulations that can be interpreted through a physics kind of lens, like the Langmuir-MacLean model or something like that, where we can interpret some physical intuition about the process. So machine learning in that sense is just a mechanism to get the data that can be interpreted, and it is nothing like a model that tells you why two things interact with each other. That's maybe is changing a little bit. People are starting to work on what they call physics-inspired machine learning, where you don't just take tanh or sigmoid or rel-u as your activation function, but use some activation function that's more physically motivated, and then maybe there are some ways to interpret what comes out of it, but that isn't usually the goal. So usually the goal would be first figure out what the system is doing, and then go back to DFT where you can put in some model calculations that you might be able to interpret in terms of a simpler model. Thanks for the question. All right, doesn't look like there are too many other questions. If you have some after you watch it, let's see. Oh yeah, I did not talk about it too much in the slide that I made about the Chebyshev. Let's see, how hard is it to get to? So we do use a cutoff radius in exactly the same way. In this line, the blue line is like a cosine cutoff radius, and that is designed to go to 0 around here smoothly. So we do exactly the same thing. There is a smooth cutoff function that makes anything outside, probably here, this is actually about 6 at 6 angstroms, anything outside of that is cut off for 0, and that is what makes it kind of linearly scaling. Otherwise, you would have something that's scaled like number of atoms cubed or something like that. So this is still like a pretty large number of atoms. At 6 angstroms can be, I don't know, 60 to 80 atoms or something like that, compared to what Lennard Jones potential is usually somewhere around 3 angstroms. Which is a fairly small number of atoms. But there's a bunch of these. The cosine cutoff function is the most common one that I've seen, but there's some polynomial ones and some others. All right, thanks. I think with that, I'm going to go ahead and end the stream. And if you have further questions, I think there is a chat connected to the video that's on YouTube. So thanks everyone for coming by, and I will see you next time.